Beautiful. Thank you much. All right, friends, let's get rolling. Let's start class together. He's coming back. Maybe Danielle will show up. All right. So let's take a moment to stop what we're doing. Get present. Let's just take a moment to bring ourselves here. We're gonna get back to the math, don't worry. Plenty of math coming your way. I won't leave you hanging on that front. So just with your eyes closed, just listening, noticing what sounds you pick up. Maybe while you're here, letting your shoulders relax just a little bit. Not forcing them, just noticing if they're tense and letting that relax if it happens, and if not, that's okay. Check out your jaw. Are you holding any tension there? I'm almost continually doing that myself, so I have to remind myself. Just letting the sounds in the room fall on your eardrums. Nothing you can do about it, it just happens. Give your fingers and toes a little wiggle, hop your eyes open. Now you're ready for math, right? Yeah. All right, so I had some questions that I asked myself because I looked at what questions might be asked. And really only one person had significantly started the web work assignment. I extended it. It's now due Monday. Yes. So it's due at the end of the day Monday. It's only like 10 problems, so it's not too bad. And I think one of them is actually like repeated in the assignment as I looked through it. It looks, maybe it was just the random generation on it. Not sure. So, one of the key things that I didn't get to define on Wednesday's class was this term. And you need to understand this, as Kiptra said, if I knew what that word meant, this assignment would be a little easier. So at least a couple of the problems on there. So let's talk about that. I'm going to restart it.
I tried starting it, and that's like most of the problems. And I was like, well, I guess I'll do the ones that I know.
Cool. Good, good, good. So remember, we have a sequence. So I've got some sequence, A sub n, and that's just a list of numbers. Just refreshing what we talked about on Wednesday. It's all new, so we'll refresh this over and over again, make sure that we're solid on these things. And I've got my index n here and my sequence terms on the vertical axis. Here's 1, 2, 3, 4. First thing in the list, second thing in the list, third, on down the way. So if I had a sequence that went like this, I'm not even going to put a formula up for it, but imagine that continuing. And this is getting closer and closer to the n-axis, the horizontal axis. That sequence is always moving down, right? So as I move from one term to the next, it's always a downward motion. Let's look at this one here. I'm going to put a couple sequences up here for you. So here's n, that'll still be a sub n there. We got 1, 2, 3, 4, 5. This sequence starts about the same spot, moves across. Oh, it doesn't go down, but it moves across then goes maybe constant for a little bit there, and then maybe on this next term it goes down. And we don't quite know what happens the rest of the way. We would need a formula to really understand that, but we'll just work with what we have here and assume that maybe this pattern, maybe it goes 2 of these, then 3 of these, then 4 in a row, then it drops 5 in a row, and onward and onward. So those runs get longer, but they're always dropping down. And let's take a look at this one. This sequence starts off here, goes up, moves across, and then starts to go down again. And then maybe starts to decrease, kind of like that one up there. So now it's going to start getting closer and closer to the n-axis. Can imagine that pattern continuing onward. So, a bunch of different behaviors happening here. This one's kind of different than the other two. This one goes up and then it goes down. This one never goes up and this one never goes up. So what I want you to just notice here is that these two sequences never increase. And then this one down here increases, stays flat, and then starts to decrease here. So from this point on, this sequence is increasing here, and then over here it's decreasing. And I'm going to say that in that weird way that I said it before, not increasing on this side. And we'll just imagine that continues on. So this behavior of never changing direction, once I start moving and I drop and I never go back up, that's called monotonicity. So these two sequences up here, these both are monotone decreasing sequences. And really what that means is that they never increase. So when you've got questions on the web work, as you do, as Cassie noted, maybe quite a few, if you've got questions about monotonicity, getting a graph is going to be really essential for that. And I've given you some tools for doing that, at least one tool that will be really helpful. We can talk about some other tools today. I'll show you how to do this stuff in Excel, which could be very, very helpful. So both these sequences are monotone decreasing. This one is not, because it ends up monotone, but it doesn't start out that way. So this sequence here is eventually monotone decreasing. But it doesn't start out that way. So one of the problems that you have on the homework is plot this sequence out. It's like a really weird one. It's got a quadratic in the bottom, something like that. And it says, where does this sequence start becoming monotone? Is one of the questions. And what you need to do is plot it out and figure it out. So for this one here, this sequence becomes monotone decreasing when n, the index, is bigger than or equal to, let's see, 1, 2, 3, 4. So there's nothing super heavy or deep going on with those questions. It's like, does this thing just like head somewhere and then never change direction? Note that being constant can't mess it up. In fact, here's the precise definition. A sequence, I wanted to give you an intuitive sense first. A sequence, A sub n, is monotone, that's an O there, monotone decreasing if A sub n is less than or equal to a sub n plus 1. Notice this is a term, and this is the next term in the sequence. So this is like left and right. And I'm never going up. I never allow for the greater than to be in that direction. So this is for all n that the sequence is defined for. If a sub n is greater than or equal to a sub n plus 1 for n greater than or equal to some cutoff point, so this is that cutoff point that I was talking about over there, then a sub n is eventually monotone decreasing. And I'll just use that little downward arrow to indicate the word decreasing. We have a flip side, so let's see, that was monotone decreasing. Similarly, a sequence can be monotone increasing if it never goes down. Monotone increasing. That's just, now I'm going to spend longer writing the word and explaining my abbreviation. That means increasing. Can be monotone increasing if a sub n is less than or equal to a sub n plus 1 for all n. So notice how this is an increase. So, for example, a sequence like this, sorry, folks on the side over there. So if I had a sequence that went like this, this is an example of a monotone increase, and you got that potential to be equal there. And you could be eventually monotone increasing if this happens after some point. The key thing is monotone whatever is about long-term behavior. So it's really all about eventual behavior. That's the key. So I recommend just plotting those things out on web work, and that'll probably make those a little bit easier. Does that make sense?
So do we just do it manually?
How do you mean?
Like just plotting it in?
Well, I gave you I put an app up on World Class to plot. And I'll show you how to do it in Excel too. And that'll give you like nice numbers, because the little app that I gave you in the announcement shows you dots, but it doesn't give you precise values. But you could use that to probably answer most of these questions. Does that sound okay? Yeah. So no, not manual. That would be, I'm not, come on, who do you think, what do you think I am? What kind of a man do you think I am? So any other questions on this? Sound good? Cool. Let me show you a little tip, because I have a feeling when you get there, you're gonna want a tip. If I had a sequence, let's say a sub n is 5n minus 1 factorial over 5n plus 3 factorial, and I wanted to understand that, and you will, right? At least twice, you're going to want to understand this in the assignment. I would think about what it means to have factorial there. So remember, if I wrote something like 5 factorial, that's 5 times every integer less, all the way down to 1. And so if n is an integer here, this is going to change on top. So when n is 1, I have 4 factorial over 8 factorial. When n is 2, I've got 9 factorial over 13 factorial. So this thing's going to change, but we can still do things in general, and that's what you need to do on this type of problem. So what I want to suggest to you is just take this moment in time to understand how to work with those factorials, because it's going to pay off in about a week big time. So let's look at that again really quick. I didn't give myself much room over there. Let's see, so I had this on top, and I had this on the bottom. And so this thing on top means 5n minus 1 times 5n minus what? 2. Beautiful. Right on. And then I would just keep subtracting 1 off, right? And multiplying that along. Does that make sense? The next one would be what? 5n minus 3. And eventually, I will get down to 3 times 2 times 1. Because that's how a factorial works. They always end with a 1. It's every integer between this number and 1 multiplied together. And then the bottom is going to be, can you take a moment, what's that bottom going to look like? Just take a moment and see if you're with me and write that out, or at least write it out in your head. I'll clean up, do some sweeping. Make sure my little story time stuff is coming back. Just changed my password because they thought I was hacking into my account because I use a VPN and it looks like I'm all over the world. So there's always weird stuff going on my account, and I got locked out of it because they thought somebody in Texas was attacking. But it was just me. So, what's next?
+2?
Yeah. And then +1. That's it. You got the rhythm. And then eventually 3 times 2 times 1. Beautiful. So now it seems like there's some stuff that might be the same on the top and the bottom, and I could cancel, but I don't quite see the end of it. Like right here, I would see that would cancel, that would cancel, that would cancel. But I need to move this out a little bit further. So let's actually extend this out. What's the next term? 5n, and then?
5n minus 1.
Fantastic. And then it goes 5n minus 2, blah, 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 down to 3, 2, 1. Now do you see stuff canceling? Lots of stuff. In fact, all the stuff on the top cancels. It leaves me with just that. And so now I can actually think about this. Those factorials are weird, but polynomials are not weird. So this is just 1 over this product. And I would just leave, oh my God, don't take the time to like FOIL all that stuff out. And it don't matter. We can do all the analysis like this. When you have factorials, never multiply them out. So we have a much simplified form. As n goes to infinity, what happens to that?
Gets bigger.
What gets bigger? I agree, something gets
The
bigger.
bottom
Bottom gets bigger. So what happens to the whole thing?
goes to 0.
Goes to 0. Yep. Awesome. So I've got a fixed quantity over something that's blowing up. That shrinks to 0. So beautiful. So now I can answer that question. And that's how you'll do at least one of them. Yeah, Kidra.
It also asks whether they're bounded or not.
I would plot them out. So this one has to be bounded. So like the only time a sequence won't be bounded is when the limit is infinity. Because otherwise you've just got finite points that you're plotting. So like if I gave you a collection of like 1,000 points, that would have to be bounded because there's always a biggest one. It's when we go to infinity and things either go up or go down like this that it become unbounded.
And then there's like options of whether it's bounded below or above.
Exactly, yeah. So if I had a sequence, I would plot it, like I said, plot them out. If I had a sequence that went like this, and I assumed that that kept going, is that bounded above? Is there a top bound on that? No, there's no ceiling, right? So this is not bounded above, and BDD I use for bounded. Is it bounded below? Can I draw a line underneath it where everything's above that line?
Yes.
And it is, so that is bounded above, or bounded below, excuse me. Let's take a look at a couple others. So here's one that's bounded above but not below. So this is bounded above, not bounded below. And in fact, the intimation here is that this sequence goes to infinity as the index goes to infinity. This one here goes to negative infinity as n goes to infinity. Let's look at one other one. Let me ask you, how could I have a sequence that's neither bounded above nor bounded below? What would that look like?
Just go both directions.
Yeah, go in both directions. Yeah, definitely. So how would I do that?
What? Like that way.
Like,
Whichever way you want.
well, that's a very vague answer, but so if I had like one sequence in every other term, it maybe did something like this. Is this what this means?
Kind of, yeah.
Okay, that's what I took it to mean. So if I had a sequence that did something like this, that would be neither bounded above nor below. And we actually saw one like that on Wednesday. It was this one where I had the sequence was -1 to the n times n. Remember that? It was -1, 2, -3, 4, and it just kept bouncing back and forth further and further. Cool. Is that feeling better about boundedness and monotonicity? I will take your lack of response as yes. Okay. Good. So this weekend, if you haven't, aka almost everybody, work on this assignment. It's now due Monday, and we can talk about it then. Clear up any problems, but don't start Monday after class. That's not going to be good. Put a little thought into it. It's not big. I think there's 11 problems. So since you came today, you were rewarded. You'll be rewarded with a mathematical tale, the greatest mathematical tale, one of the greatest I know.
Today?
That's what today means. Absolutely, yeah. I might not have said the word today, Liz, so I'll take back my snide remarks and put them in my pipe and smoke them. If that's what you do with snide remarks. I gotta have this thing call me, so just give me a second here. First off, I have to look up my stupid old password. Okay. So you are in luck. Yeah, it's gonna be today. You can escape while I'm not looking. 5, 2, 3, 4. Now I'm just reading my password out. Great. I trust you all. Fantastic. Oh, good. Oh, now call me. Okay. Yeah, there's the call. Okay, and I'm in. Outstanding. And I guess we'll just take our time and let that roll. So we can close all our laptops and electrical devices while I tell you this tale. You can start that all in 35 minutes. Tops. Cool, so I want to tell you about a model, like one of the most important models in science, absolutely. And it's called the logistic model. And let me show you how this works. It's really a great population model, a very simple one. But let's say I have some population of critters of some kind, and they have this max population that they could ever reach. So right here, this is called carrying capacity of the population. And that just means the most that the environment can sustain of these little creatures, big creatures, whatever. And it's kind of, we'll think of it as maybe like a percent or something. So this would be like 100% here. And I'm going to indicate that with a 1. And then this is 0 down here. So if I put this dot here, this would indicate there was no one in the population. This would indicate, a dot right here would indicate the population is at utter max capacity and there's no more room for sustaining life. This curve here gives us a decent model of how generational change can occur. So for example, if we are at generation 1, let's just say that, and the population is pretty close to carrying capacity, there's not much room for growth. So you can use this curve to figure out what the size of the next population will be. And it would be that amount right there. And now we're assuming there's like birth and death, so this distance here is a little bit bigger than that one there. Right when we're halfway, so when we have half the population filled and half the remaining space to grow, that's when the population can grow the fastest, because there's reproduction happening with the things that already exist, and there's plenty of space and resources to sustain them. So right there is where we could get the biggest generational increase. So this is like Gen 1, and then this would be the Gen 2 size right here. Is that making sense? Yeah. So really simple model, and it's a parabola, so that's really lovely. It's absolutely lovely. And let's label some things. So let's call this X sub n, and that just means current gen, or gen n, how about that, generation n. And then we'll have up here generation next generation, X sub n plus 1. So I can get like a sequence of population levels. So I start off maybe here at like a quarter, right? That's about a quarter, and this is a half, 3/4. So I start off at 25% capacity. And then I wonder, what's the size of the next generation? I come up here, and that looks a little bit under 3/4, right? Does that seem right? So the next generation is going to be, let's just say 3/4. And then I want to find the next generation. So I take this value here and I plug it back in. So here's 0.75, what's the next generation going to be? And it looks incredibly large. So 0.8. So we've grown a little bit. But notice how we're slowing down, right? There was a big jump when we had the highest possible growth rate, and then there's a smaller increase. So then at 0.8, when I input that, I see that I have an even less increase. In fact, I've gone down. So the population actually went down on the next generation. That maybe looks like back at 0.75. And it kind of, if these numbers were true, what would be the next population level? Oh wait, so look, so 0.75 took me to 0.8. 0.8 took me to 0.75, so back to 0.75, right? So because 0.8 would take us to here, and that gets us this output level. So this would just kind of alternate back and forth. And so every year you'd see a lot of them, and next year you'd see a lot, but slightly less. This is the kind of thing with the cicadas, right? The 7-year cicadas, the locusts that come every 7 years. It's kind of something like this. There's just, they hibernate and then they live underground for a period of time, and then they pop out, and then they all die and have a chance to reproduce, and the populations ebb and flow. Sunspots do something like this, but I don't know if sunspots interact with each other in this way. Probably not. But we have an 11-year sunspot cycle, right? So every 11 years the sun has, and sunspots are those cool spots on the sun. They look really dark from here. They're like, they just let, they're like actually deep red, but they look black from here with a telescope, with the appropriate solar lens on it. So I could use this model to do population predictions. Let me show you a cool way to think about the thing I just expressed there. If I take the perfect diagonal here, so this is x sub n equals x sub n plus 1. That's the perfect, that's like y equals x on here if you think about x and y. What you can do to determine the growth here is a thing called cobwebbing. So let's say I went to 0.75 and I go to the parabola. Now to get the next output level, I go over to this diagonal and then come back down. Oh wait, I guess that was the 0.8 probably right there. And then come back down to the parabola. And that gives me the next output level. So this was the one where it was 0.8 and then I went here, and what does that level correspond to? Well, you just go to the diagonal and you bounce yourself back down. 0.75. So it's the same thing as doing this, taking the output from here and putting it down here. Think about what I was doing. I went up to see how high we went, looked at the value over here, and then just flipped that value back down to here and used that as the input. So when I do this process, I get things that look like this. As I said, this is a cobweb. So come up here, I go to the parabola. I always go horizontal to the diagonal, down to the parabola, back to the line. Now this one's changing a little just because I picked a slightly different condition. But here we see the populations kind of ebbing and flowing, but they're also changing in kind of unusual ways. So what would this look like? Well, one year I've got a low population, the next year a high population, and then the next year an even lower one and a higher one. And then it's kind of bouncing back and forth. There's almost a stabilization in these two outputs right here. So you end up with a cyclic pattern. It doesn't always have to be like that. In fact, let me show you, well, let me give you the official equation for this. So the next generation is equal to this growth parameter times the previous generation times 1 minus the previous generation. So like if you plotted out this, you would get a parabola that had intercepts 0 and 1, that opened downward, and r is going to be a positive number. And as I change r, as I change this number in front, it changes the shape of the parabola. If r is large, it looks like this. If r is small, it looks like this. So it can just, that kind of makes sense, right? It just scales the y values. So this is small r, this is large r. And this tells you just how fast, how reproductively active the population is. So, with that in mind, let's take a look at some stuffs, some computer aids here. And I guess stay signed in, my God, please don't make me do this again. Okay, and I'll have all these apps in there if you got the weekend ahead of you and a semi-small assignment, so you can just like have a field day with this stuff. So there's that sequence plotter, Vivian, that I was talking about, just that first, you can't see it, I guess, can you? No? Yeah, exactly. Use your imagination. Imagine a computer screen. Ooh, yeah, there we go. So that's like the setup for the story. The story's really not happened yet. There we go. So yes, so this first one right here, that's the one I'm talking about, sequence plotter. And then underneath this, we've got, from the Complexity Explorer website, and gee, I forgot how great our internet was. This is not super complicated stuff. Come on, Reach. I'm gonna copy that. I'm gonna paste it here. Do this and go back. I'm gonna open other things so that we have time for them to open. Wunderbar. Okay, so here's the growth curve that I was talking about, the parabola. Here's the diagonal line, and here's the cobwebbing happening that I was mentioning. Go from an initial, this one looks like it has an initial state of 0.2, and indeed it does. There's the initial condition. I literally could not have changed that by just touching this. Okay. My God. Come on. Oh, dude. Does anything work?
It's because it's Friday.
I think so, yeah. Kind of getting that vibe here anyway, yeah. It's theoretically doing something. I don't want to stop it. Is it there? Oh, okay. I don't think I freaking touch that. So initial condition is 0.2. Okay, go just like scoot, just scoot. I'm not clicking, I'm not doing anything. Okay, there we go. So an initial condition of 0.2, this is the growth parameter 3. So that's the thing that as I change it, it makes the parabola more steep or more shallow. This is just the number of generations we want to see. And over here, it's showing us from generation to generation what is the size of the generation. So you're seeing that oscillation here. And notice how there's a big swing at the beginning, which you can kind of see over here, and then it settles down to kind of a steady state. In some way, two steady states, a cyclic steady state. This is called a two cycle. There's two different things that we cycle between. So now watch what happens as we change the growth parameter. Now, first off, let me show you the initial condition, how that affects things. So let's say at 0.5, we had 50% of the possible population. And then I guess I have to say restart simulation. Notice how it actually has the same behavior as the other one. Now let's see, what if we had a really large population? Like what about 0.9? How about type of 0.9? And then I say restart, and look, it kind of does the same thing. For the most part. Kitra, you were, yeah?
Yeah.
Yeah, so like I would look over here to like see the output, because that gets a little messy over there. That's kind of crazy. But notice how no matter where we started, the end behavior was this two cycle. Well, that's interesting. What happens if I change the growth rate? So let's go to, say maybe, let's drop the growth rate down. They're much less randy, if people still use that word. Oh, look at that. So now the population is not reproducing as fast. It's 0.2. It's 2 is the growth rate as opposed to 3. And now I see it just kind of reaches a steady state. And in fact, that looks like the 50% mark right there, right? So the population grows and then stabilizes. Never really changes. There's enough resources and enough birth and death to keep things at a single stable rate. So that's like a one cycle. And I'm going to open, no, I'm not going to open another app. Let's increase the growth rate past 3. So how about 3.2? Oh, I guess I need to click that button. Ah, what happened? What's different here from 3?
The highs and lows are a lot more, a lot wider.
Yeah, more extreme, right?
Yeah.
More extreme oscillations from generation to generation. And here we're reaching 0.8 and then down to like 0.55 or something like that. Let's crank it up a little bit more. So that's 3.2. How about 3.3? Same thing, kind of a little bit further, right? They jumped a little bit further. So let's go to 3.4. Restart the simulation. Okay, now something really interesting and subtle is happening here. You see that we now have a really wide swing from generation to generation, But look what it's kind of doing at the beginning. Notice how there's another subtle oscillation starting in this one, and kind of up here it goes up and then down and then up and then it settles. So there's like, it's wanting to give birth to a new kind of thing besides these two things here. Let's increase the parameter just a little bit, and I'm not going to increase it much. I'm just going to go to 0.41 and restart the simulation. So notice the beginning, getting a little bit more extreme. Let's go to 3.43. And that looks about the same. That's not terribly interesting. Let's go to 3.45. Oh. Yes, Lou.
Why is the oscillations at the bottom more drastic than on the top?
That I don't know, but I'm assuming it has something to do with just where this intersection is here. It's kind of toward the right of that parabola. So like just geometrically, I think that's what's happening. Why it would be happening in a population, I can't say. So that's a really interesting observation. But notice here that we're splitting even more. Each of these 2 cycles is splitting into its own 2 cycle. And then that seems to be slowly dying out. But what if I go up just a little bit more? Notice my increases are becoming smaller and smaller too. Those are becoming, I think if I get to 4.9, we're gonna have some craziness. Oh, see, now they're growing. The 2 cycles are splitting. Now there's a 4 cycle. Now there's literally 4 different populations. Like every 4 years, we see the same thing happening again. We have this generation, then it jumps up, then it jumps down, then up and up and up. So we have 4 different populations that we witness happening over the years. What if I go to 4.9 and restart? They are exploding in a different way. Let's go to, I'm gonna go to 3.5. I'm a little scared here. Not like really scared. Let's go to 3.6. See what happens. Oh, okay, that was too far. Too much. 3.52, let's try that. Well, that's, how about 1 decimal point would work? 3.52. Okay, so the 2 cycles are expanding even more. Let's go to 3.56. Restart simulation. What's happening? Splitting again. So again, now the 4 cycles are each splitting into their own 2 cycles. So what we're witnessing here is something like this. If we were mapping out equilibrium states in this population, we would see that for low growth values, so this is my growth rate, R down here. For low growth rates, it kind of stabilized. It went up and then it stabilized to 1 generation or 1 population. And then we hit that like 3.4-ish, and it split into 2 possible populations, and it alternated between those. And then these grew further and further apart until at some point they split themselves. And now we're seeing them split again into 8 possible populations, so each one of these split again. And notice how those little pitchforks get tinier and tinier each time. Let me just 3.58. So now they're really far. I think there's pretty clearly 8 different populations going on there. Did I do 5.9 yet? Oh boy. Now that looks like a real mess, doesn't it? Do you see any patterns? There's kind of a top one and a bottom one, but it's really hard to see that there's any rhythm in this picture. I don't see it. I'm not seeing any rhythm. In fact, it seems like there's no equilibria at all that I can discern. Let's see if we can actually get more iterates in here. I don't know what this does if I say like 100. I haven't done that. Oh, ooh, there's some kind of pretty patterns happening there.
Little arrows.
Yeah, little arrows forming. Let's go to 3.6. I think that was where things looked really whack. So, oh my. Yeah, Kitra.
Is it like a thing that, I don't know if you could see the first 2 points
I'm
the
sorry.
entire time?
Yes, I'm gonna go back to that. But
Or like, there were no other points that went outside those first 2 original like population values.
They were all kind of bound
Yeah.
between those?
Oh, yeah.
Yeah.
Is that a thing?
It
Like,
sounds reasonable. It sounds like a thing.
Because carrying capacity is like, you can't exceed one limit, and so no matter like how like sporadic things are, they'll like stay below.
Yeah.
Yeah. That sounds pretty good.
So then, like, even if you consider like the first box, how it was like 0.2, 0.9, all the values in between, no matter how large R gets, will stay between those two.
It sounds pretty reasonable. Yeah, sounds like a decent hypothesis, worthy of further exploration. So here's the Yule cobweb picture again. But what's interesting here is I've got these initial states. So this green one is if I started at some different initial value, and hopefully I can scoot that. I thought that I could. Oh, I can. It's just terribly slow. But notice how with, let's see, what is R at right here? Can you even see it on there? It's just my eyes. Oh, it's down at the bottom, 2.7. So it says lambda, but that's our growth rate here. No matter where we start, the end behavior is the same, right? So the long-term behavior for this growth rate of 2.7 ends up being the same. Things jump up and then they jump down, but then they settle down into this single state right here. And then let's increase that lambda and see what happens. So let's bring that up. And we're starting to see they're still doing the same thing. It's taking them a long time to spiral down is what's happening. That's why it like looks so dense in there and thick. Let's keep going. So where am I at? Is that 2.79? Oh, now it's actually acting quite well. So now we're at a 2 cycle. We're bouncing back and forth. The thing to look at is this top and bottom border. These are your end up populations, bouncing back and forth between these two. Or you can look at the sides. But only look at the top and bottom or the sides to determine what your ultimate end behavior is. Now look, and this happens no matter where I have my initial conditions. It kind of does the same thing. It just takes a little while. So now let's crank this up a little bit more. And now, do you see them splitting? So we're splitting again, and now watch what happens. I'm gonna, oh boy, there was some super splitting. So right now, this is at 3.45. Things are getting so crazy that it's really hard to tell what's happening. And then right here at, I can't see that value because of my ancient eyes. But right there at that value, things become completely unpredictable. This is chaos. Now what I want to show you is that this has sensitive dependence on initial conditions. So now check this out. If I start at the same spot, of course the same end behavior. I'm going to run just a little late here, just a few minutes, so you just got to bear with me. But just a subtle change in the initial condition results in long-term changes in the final output. Let's see, let's get down to here. Oh, here you can really see it. So just a little bitty change in where I start changes my long-term behavior. And if, let's see, was that 3.7? Oh my God, that's crazy. There we go. This is the butterfly effect. If you've ever heard about the butterfly effect beyond that horrible movie with Ashton Kutcher in it from the past, this is the butterfly effect that when I have a dynamical system and in a chaotic state, and that's what we have here, that small changes in initial conditions result in long-term changes in outcomes. Now I've got one last thing to show you, like I said. And it's, this is not, I want to show you that bifurcation diagram, because what happened is at some point we hit chaos. And this thing becomes crazy here. There's no more pattern. These bifurcations start just coming more rapidly. So each of these things keeps splitting faster and faster, and it looks like, the crazy infinite devil's pitchfork. It's just so beautiful. And I'm going to show it to you if Regis will allow me to show you.
Come on, Regis.
Come on, Regis. Come on, Regis. That's cobweb diagrams. Come down. That's not the cobweb diagram. Okay, hold on. God help us now, we're going into the Wild West here. Logistics bifurcation diagram. Aha! Wonderful. And then I have one more thing to show you after I show you this picture. So there is the full bifurcation diagram. There it will be. There it's coming. Yes, yes. Do they just?
Oh, there it goes.
Stop.
Is it coming?
Yep.
Yes. Aha. Look.
What?
So, look, this is like one of the most beautiful things. So I do mathy T-shirts. This is like one of my T-shirts. I took this and turned it into a tree because it always is so beautiful. But here you see the splitting, and then the splitting becomes faster and faster, and these bands of haze are the chaos. Right here, you can't really see it, but you're about to because I'm going to show you a zoom in. The whole picture repeats. This whole thing appears within itself over and over and over again. It is a fractal. It is a fractal. So let's just look at one last thing, and this is, you need this for your Friday. Okay. So this is zooming in on that diagram. And I think there's nice music. There's like some beautiful piano with this one, because I've watched this video like 10 times a year for the last. Yeah,
So I'm
Josh.
gonna head out. We have practice at 3 o'clock.
Okay, all right, go. You're gonna have to watch this on your own.
Definitely will.
Will you? Are you going to, Josh? You
Yeah.
didn't lie to me.
Yeah, why not? I'll just watch the recording.
Okay, there we go. Fair enough.
51 minutes.
Okay.
I'll watch
All right, fair enough. All right, thank you. Thank you. Okay, here we go. All right, so, beautiful. We don't have music. We'll just watch the Zoom. I'll just send this to Josh, so he doesn't have to do anything special. But this is, yeah, zoom up to, what is that, a billion? Billion times closer. See it again inside of itself.
Okay, I have another question.
Yeah.
Sorry if I continue to go. Okay. So the biggest line, like the single line that leads to the
Yes.
first fourth, if
Yes.
you continue that, it goes to what looks like the cross section.
Yeah.
Why?
That's a good question. I don't know if I know the answer to that. This
So it
is.
just keep.
This gives me anxiety. I don't know why. It's really stressing me out.
You seem to really have an issue with infinity.
My dad one time was showing me those like little fractals to like Grateful Dead songs, and I cried.
I wish I'd thought of that. Maybe if I put that on, Cassie would feel a little bit better. I could put on Ripple or something like that.
They're rich in my
I know about this.
So,
Oh my God.
at this point, it's starting to break down because the computational precision of the machine is just being reached. Like it literally, this would
It
keep
just
going
can't
forever. It can't.
handle it.
It just can't do it. So that's why now watch. Now, Cassie, you might want to close your eyes on this.
It's gonna zoom out really fast.
Yeah, they're gonna zoom out.
Okay.
So
This reminds-
everything's okay. We're coming out.
This reminds me of like the space videos where they like start out like really far and then they start zooming into
yeah.
the Earth and like.
Yeah, absolutely.
So it's just like.
This is so
repeating
cool.
itself.
Yes, forever and ever. And if we had infinite precision, we could see it.
So there's no limits.
No limit. Never
Also,
ends.
is this like the little triangle where like it's like multiple
Sierpinski triangle,
Sierpinski?
absolutely. Yes, it is. You're right, Lou. Lou's done a lot of recreational math, so he's well versed in this. And I love these dark lines always. They're so interesting. I don't quite understand why they're
So it's
like.
completely random?
No,
No?
not random. Completely deterministic, but sensitive to initial conditions. So there ends up being no pattern. There's
Why does it-
difference.
why it has to
What's
zoom
that?
out?
Oh, then there's the hidden part. Cassie, don't look.
I was gonna
There's
say, what
a-
is that?
There's a hidden side to it, the
Hidden
anti-side.
Oh my god.
There's an opposite.
There's an
Oh,
opposite
It's just
side.
reverse.
Yeah.
And that's all I have to show you. No, we're not.
I'm like,
gonna
wait,
watch
that's so cool.
that. I don't have my good friend Josh to help me out right now.
Wait,
Yeah.
that's so cool.
Okay, there we go. Good.